Hello and welcome to Science On. You're watching live, interactive and international science stream. My name is Oliver and I'll be your host for tonight. Tonight's theme is vibration, and you can expect 6 performances from 6 brilliant performers from all around the globe to showcase their most favorite experiments involving, you guessed it, vibrations. After that, we will have a discussion session to make it even more interactive, so you can interact with our guests through comments and questions. But first, let me tell you a little bit more about Science On. You can watch this stream thanks to the efforts of 5 science enthusiasts that believe that we should use every way possible to promote science and to share our passion with experimenting and subsequently, hopefully, learning something new. You can watch Science on major social media platforms and also follow us there, with the most active being YouTube. At this point, I would also like to thank our partners. The institution that makes these streams possible from technological standpoint is Vida Science Center. And also I would like to thank our dear friends at YITS, South Moravia Innovation Center, and their innovation ecosystem, #Brno Region. And now let me introduce tonight's guest. And let's start with Chris joining us from the USA. Hello, Chris, can you hear us?
I can see you and hear you perfectly.
Perfect, thank you, Chris. Originally, we were supposed to also be joined by your partner in Science Entertainment, Diane, but unfortunately she's traveling right now. But we will see her in some form, is that correct?
You will see her in our video, which we had a great deal of fun making. By the way, Diane just wrote me. She's on a beach in Mexico.
Okay. Okay, so we are jealous, a little bit jealous here, but hopefully we'll have a lot of fun. Thank you, Chris. Next, joining us from a completely different time zone is Stuart from Australia. Hello, Stuart, can you hear us?
Hi, Oliver. Yes, I can. And thanks for having us all together. And good evening, Chris. Great to see you again.
Thank you, Stuart. And can you tell us a little bit more about what we can expect from your performance?
So I'm going to lead the group off tonight. I'm going to introduce some basic ideas about vibration. And I'm going to, I guess, share my passion about how I find connections between simple aspects of science and relating them across what might seem to be some very different topics. So we'll be looking at noise-cancelling headphones, greenhouse gas, and pH indicators, all together.
Wow, that sounds super exciting. Thank you. And next, from now Switzerland, but originally from Slovenia, it's Anja. Hello, Anja.
Hi. Good to be here.
Can you tell us? Well, thank you for being here. Can you tell us a little bit more of what can we expect from your performance?
Yeah, I'm going to be diving into one very popular book and film from a few years ago, so Angels and Demons, and I'm going to show how we trap some antimatter at CERN, so going into a bit more complex topics.
Wow, sounds super exotic. Okay, great, thank you. And also from abroad is coming Michael. Michael, where are you now?
So right now I'm joining from Tineo, Spain, which is on the Camino de Santiago, which I'm currently walking.
Mm-hmm. And so on this tour, what can we expect from you?
So kind of a full 180 from Anya, going from something very complicated to simple. I'll be using toilet paper and my headphones to show my favorite kind of vibration, which is sound. And we'll be looking at how fast sound travels through this roll of toilet paper.
Okay, okay. I'm really excited about it. So thank you all. And our next guests are actually from Czech Republic. So I would like to invite them to my physical stage. And first is David from Vida Science Center. So hello, David.
Hello, Oliver.
And can you please tell us, like, what can we expect and what can we be looking forward to in your
Yeah, sure. I will try to move things using sound, and exactly it will be Helmholtz resonance. So we'll see if it will work. Hopefully, yes.
Perfect, perfect. Thank you very much. And the second one, and last but not least, also from Czech Republic, but this time our very own, with ever more majestic beard, is coming, Adam. Please come to our physical stage. And Adam, please tell us vibrations. How have you incorporated them into your experiments?
We're gonna levitate.
Oh, levitate.
That's the thing, yeah.
Vibrations. Okay, that's...
With vibrations, yeah, of course. Yeah.
Okay, so I think it's a lot of to be looking forward to. And right now, please let me get back to our audience and to remind you that please have in mind that this is a interactive stream. And to make it interactive, we actually need your help. So please don't hesitate, never hesitate to answer questions from our guests, or just to ask your own questions or post comments on any platform that you are watching this stream on right now. We will gather all the comments and put it either during the performance or at the end at the final discussion session. But now I think we're ready. I think we're ready to officially start tonight's Science on Stream vibration. And our first performer is Stuart. Welcome again, Stuart.
Thanks, Oliver.
Great to have you here.
And
sorry, Stuart. Yeah, I'll just ask you a few questions if I may.
Yeah.
And for example, in what time zone are you now? Because I heard you have a very strange time zones in Australia. So are you in one of those interesting ones, or just the boring ones, full 1 hour? What time zone are you in?
All of Australia is interesting. The time zones is not the real reason to come to Australia. So I'm over on the East Coast in the nation's capital, and it's just 3 a.m. in the morning. So if you see me drinking coffee, you'll understand why.
Yeah, sure. Okay, and Stuart, you've been in the area of science communication for quite a long time, if I may say it like that. And we have evidence for that. Can I get the evidence, please? And can you tell us a little bit more about what we can see on the picture that's coming right up, I hope? Yeah, we will wait for the picture. Oh, here it is. Can you please comment a little bit?
So this I've been doing science communication for quite some time. This is a photograph for when I had more hair and less face. And I'm meant to be explaining to Prince Charles, this is about 1986, in the very small science center that we started as a volunteer community-run project. We're now a national international science center in Questacon. So I was meant to be explaining bone stress in kangaroos to Prince Charles, but I pulled out from behind a brick a coat hanger and some string, and I got Prince Charles to wrap his fingers around the string and put it in his big ears. Everyone always commented on his large ears. And to bang his head against the wall so the coat hanger would hit and vibrate. So I've been dealing with vibrations and misbehaving for quite some time, Oliver.
Okay, thank you very much for explaining this. And now the stage is yours. We're super excited to see your performance.
Thanks very much, Oliver. And thanks to everyone in the Science On team for all this great work above and beyond sort of what is expected of mortals to carry on. Because I'm leading the session off tonight, I thought I would lead us in to just a couple of quick reminders about what vibrations are, so that we're kind of in that headspace while we get all of the other demonstrations. So for a large amount of my slot tonight, I'll be working over on my little video bench over at the side, and we've got set up over there. Let me just get this running for us. There we go. I've just got a vise and a blade out of a hacksaw, and just a normal hacksaw blade. We're kind of familiar, these are very whippy, and so we can see a simple vibration. I've just got a pink tag on the end so we can see what's going on, and we can see a simple vibration. I've got here a heavy magnet. I'll put that onto the end of the hacksaw blade, and much slower. So we've seen with vibrations that if we add weight, mass, to that, our vibration will slow down. The frequency will slow down. If I make that shorter, we've all played with rulers in schools, sort of hitting them on the desk. I've made it shorter. The vibration speed, the frequency has gone back up. That's because it's now stiffer. Force equals mass and acceleration. So we put more mass, the acceleration is slower. We make it stiffer, more force, the vibration will go faster. So that's kind of a quick reminder for many of you. I'm sure you're all familiar with that. But what I would like to do now is pose a little question. So here I've just got a tin can, somewhere between what Michael will be doing with the toilet roll and Anya and quantum entanglement, a simple tin can with a rubber band. And we've all sort of played with rubber bands. I'll just stretch it across the top. We get a note, it's vibrating. Like Michael, I love sound. Pull it tighter. Make it looser. A lower note. So my question to kind of get the evening started is, if I start plucking the rubber band and start stretching the rubber band out, will the note go higher, or will the note go lower, or will it do something else? What's your thoughts about that? So if I pluck the rubber band, I've got that low note. If I pluck it when I've got it pulled out, what will the note be? Will the note move higher, note move lower, or do something else? What are your thoughts? Higher, Tobias has come in with things higher. And one of the things I love about some science provocations, a friend of mine uses the term provocación. Sounds very sexy in kind of Spanish, a provocación, is to find things which we think we understand, we've seen it every day, and just to get a closer look and just trigger that closer inquiry. I'll give people higher. Okay, we've got that. That seems the logical thing. We'll give time a little bit more. Any more comments? We've got higher. All right, let's try. Just move the microphone off stage so we can see that I am stretching the cable, the rubber band. All right, now probably twice as long now. Let's try that again. Twice as long. I don't think that's going much higher. I don't think that's going much lower. In fact, unless I really stretch the rubber band, that note is going to stay the same. And what's happening with this is, sure enough, as I stretch it, it's tighter. And if that was a guitar string, the note would go higher, but I'm also making it longer at the same time. And those two effects cancel out. So one is making it higher, others making it lower, it stays the same. So there's just something to try. Just get a rubber band, put it against your ear, and see what you hear. We're talking about those two things cancelling out. Here, something which every international traveller has in their bag if they can, some noise cancelling headphones. for those of us which spend too much time on airplanes, these are kind of, you know, gold, cancelling out the noise. But have you ever wondered how they actually work? So my next little activity, we're just going to set up here. There we go. So this is just like a PVC pipe, and I've made this a little bit like a trombone, so I can slide one side out. So this is all open. We have a speaker here. Let me just go and get that restarted for us. Just have to get one thing going. There we go. And I've got the speaker here. We've got the pipe connected so the sound can go all the way around and meet at the other side. So what we'll do now, I'll just bring the microphone.
Hey Stuart, I have to stop you for a little bit because we can't hear you, which is a pity in science experiments that involve sound. So could you please check?
Am I back on now?
Yes, you are back online.
Okay.
So could you please start over with this experiment?
Sure. Sorry about that. I bumped the wrong button. So what we'll look at now is an activity about noise cancelling headphones and just how they actually work. What I have here, just a PVC tube set up, a little bit like a trombone. On one side, I've got a small speaker, and this is all open so that the sound can flow all the way around and come out this side. Now that microphone which I bumped before, there we go. And on the phone, I've got a little frequency generator so I can make particular tones of music. So we'll put a reasonably high one on. Now hopefully you can hear that. And this is all open. Let's just see what happens as I slide the trombone out. So you should hear that now. Almost gone. Try that back in, high. That seems a little bit strange. What's going on? Let's go and visualize what's actually happening. And to do that, I'm going to drop the lights down and we'll see the sound. So the sound is coming in. The sound is compressions and expansions of gas. That's what we're visualizing. Coming around and meeting here and coming out to us to hear. All right, so that's what's happening at the moment. But when I pull the tube out, let's go and see what happens when I stretch that tube. It's very quiet. And now, because this wave has further to go, those pressure waves are not meeting together, they're meeting out of step with each other. So rather than having high pressure sound wave meeting, they actually miss each other and cancel out. But that's only because I've got this tuned to exactly the right frequency, one which matches the length of this pipe. Let's just put the lights back on. Back in, nice and loud. I'll put a different tone, a low note in. And hopefully you can now hear the two notes. Let's see what happens when I move the trombone slide back out. We've lost the high pitch note and the low note is still coming through.
Stuart, sorry to interrupt you.
Yeah.
Again. These sound experiments are very tricky in the stream, and right now, unfortunately, we can't hear much of a difference in between the longer tube and the shorter tube. Could you please try putting the microphone that's picking up the sound closer to the exit of the tubes?
Yep.
So maybe this will help.
So at the moment, we're just back one high note. You hearing a difference there, Oliver?
Yes, now it's clear, loud and clear. Thank you, Stuart.
No, no problem. Thanks for letting me know. But now if I put the low note on as well, we should hear both notes. But now we've got rid of the high one and we're left mostly just with the low note. And so we can filter those out. And noise cancelling headphones do very much the same as that cancelling. They just use electronics to detect the incoming wave and create an opposite wave and cancel them out and give us quiet to listen to what we do want to listen to. Let's just turn those off. What we'll have a look at now is we've looked at some of those vibrations. One of the things which I spend a lot of time dealing with is in fact looking at environmental science and hands-on activities. And we've all heard about greenhouse gas and climate change. Here is a model that I have of carbon dioxide. And one of the reasons carbon dioxide is the greenhouse gas it is because of vibrations. And CO2 molecule vibrates very much like that at a particular frequency. And that frequency matches infrared. So infrared light, infrared radiation has a particular frequency, and CO2 vibrates at that frequency. So infrared light, infrared energy reaching the planet excites carbon dioxide in a very particular way. And that's why it picks up that energy. That energy gets translated into heat, and that's the source of greenhouse gases. I'll just very quickly do one little demonstration. We'll take my special CO2 exciting device. So we've got two of these, two CO2s, very much the same. And if I vibrate the stick at the right frequency, I'll get the CO2 to vibrate. If I just add now a little bit of weight to one of those, I'll change the frequency. So now I can get the top one to vibrate at one frequency, but the other one's not really vibrating. If I go a bit faster, I can get the bottom one to vibrate, but not the top. And so different molecules with different masses, different atoms, will vibrate at different frequencies. And that's one of the things behind our use of pH indicators, those coloured ingredients that we add to tell if something is an acid or a base, if it's alkaline. Those chemicals in an acid get protons added to them. That makes them heavier. They vibrate slower. They change their colour because of that. And if you look at all of the pH indicator charts, you'll find most of them, almost all of them, will become red at an acid. And that's because those protons are making them heavier and vibrating slower, which matches the red end of the spectrum. So I'll leave it there for tonight. I look forward to seeing all of the other interpretations of vibration, and I'll hand back to Oliver and the team. Thanks very much for your time. Hopefully that gets you to look at the world slightly differently.
Thank you, Stuart. Thank you, Stuart. I'm really grateful that you brought even environmental impacts of vibration to the stream. It's great to have such a broad spectrum of effects of vibrations. So thank you for that. And also to our audience here, you've picked up some answers in the internal stream, so thanks for that. But our audience did not see it, so we'll just bring up some of the answers to your question. Again, the question was if the note would be higher or lower frequency depending on how you stretch search the rubber band. So we got some answers. We should be able to see them now. And this is not the right thing to pop up, but these things happen in streams. And this is live. You can see this is live. So we had higher from Tobias, and also we'll go higher from Camille. So this is what you hopefully will expect in other performances as well, that your answers will be here. And we can see that all of them just went for higher, as you said in your performance. Okay, Stuart, and getting back to you, you have on your T-shirt Science Nomad. So this is title that you yourself refer to you. And what does it mean to you? What does it mean as a community? And can you tell us a little bit more about it?
Yeah. So for 40 years, I worked in our science centre, helping it become established and grow to a wonderful large science centre with a lot of outreach. I took early retirement and took all of those skills so that I could then go and share hands-on learning with communities that didn't have the resources that we have here in Australia. So I spent most of my time in Southeast Asia, sometime in Africa, and other emerging countries like Singapore. Mostly working with teachers these days to go and get some catalytic change with that. So I bring hands-on learning and inquiry and sort of interesting provocations like the rubber band. I have a saying, sort of humble materials, powerful learning. So that's what I do. When I can, embassies will take me overseas. I'll work with universities, professional bodies that train teachers or just schools, and do that sort of work. So in a month's time, I'll be going to back to Bangkok to go and work with an orphanage that looks after girls at risk to introduce STEM programs with those schools. So I keep busy that way.
Okay, great. Thank you. Thank you very much. And also, I would like to ask maybe a more technical question about how is it performing to a camera instead of a live audience, because we see that you have a professional studio there, or semi-professional, with all these perfect visualizations. So how do you feel about performing to camera?
Look, I always prefer live. Face-to-face in the flesh. There are things you can do, the reactions with the audience, particularly for the sort of work which I value, which is stimulating thinking. And so while we've been getting some great participation with questions and answers tonight, which is great, to do that face-to-face gives you so much more opportunities to work with people as they make sense of what you're sharing. So I don't teach very much, but I provide learning opportunities and stimulate with questions. And so doing face-to-face is much better. But we've all learned that online is worth doing as well. So I could never be reaching your audience if I had to travel. So it's great to make use of it.
Yeah, definitely. Okay, thank you very much. I believe we will get to some similar questions at the discussion session at the end. So for now, thank you, Stuart, and I will see you later. And I would like to remind our audience that you can always ask questions in the comments on any platform that you are watching this stream on, and we will continue. And our next guest is our physical one. As you can see, I have some physical props here, and it's David. Welcome again, David.
Hey.
And you have worked at Vida Science Center for quite a few years. Is it 6 or 7, something like that, right?
Yeah, something around 7 years now.
And it's a part-time job for you, correct?
Yes.
Yeah. And so you are finishing your studies?
Yes, this year, like in 2 months.
Okay, and can you tell us a little bit more about your plans after you finish your studies?
We'll see. I will try to find a full-time job, maybe. I'm hoping that I will find it in Brno, so I can still sometimes participate in these streams and etc.
Yeah.
So.
And in what field?
Field, I spent 6 years studying something, so I hope that it will be like this biotechnological field.
Thank you. And also we have some evidence of your past science activities, and I believe you're excited to see which one we chose. So I would like to get the picture on screen, and I would like for you, David, to comment on what is going on in this picture.
Here you can see me as a plumber, and I was explaining how toilet is working, and I think you can still find this video on Vida's YouTube or Facebook channel. I'm not sure, but yeah, it was a great time.
Okay, thank you very much for explaining. And now it's time for you to perform with these props. So the stage is yours.
Thank you very much, Oliver. Okay, so hello one more time. And I talked about Helmholtz resonation. And I was talking about propelling stuff with sound. And it is best to just begin with the experiment, and I will show you the best thing I can show you here, and then we'll talk about it. And actually, this is a DIY system that you can make yourself at home. So hopefully, some of you will try it at home after you see this. So here we go. Or not. Yeah. Okay, so there was some loud noise, and as you can still see, the bottles started to rotate from my point of view clockwise, but it doesn't matter. But why? What's the thing behind the rotation? What causes it? And that's a question for you. So what is causing the bottles to rotate? And you have 4 options, and I hope, yes, you can see them on the screen. So what is the thing that's propelling these bottles? Well, it can be air from the speaker, because the speaker itself is vibrating, and maybe it's moving with the air, and the air is pushing the bottles, and so they rotate. Or it is air from the bottles that is propelling the bottles forward, or it's a sound wave from the speaker that is propelling, or I told you already that this is DIY. There can be something that I'm pulling on, and the flasks can then rotate. So time for you to choose your answer, and I will start to explain this experiment a bit, and you can keep answering, and in the end we'll get back to the question, and we'll see how you were answering. So sound. Can sound move things? Well, most of you probably felt it yourself. If you are in a space where it's really loud music with deep sounds, with deep frequencies, you can hear, you can even feel the vibrations on your body. And that's because sound travels through the air as a longitudinal wave. And I can show you how does that longitudinal wave look like. I will move this aside, so I have some space here. Yep, don't mind me, just making space. Okay, so here I have a spring. Maybe if you are long enough with Science On, you could see me with another type of spring earlier on. But this is black spring, and it will serve me well. So here is air. Okay, the spring represents air, and I will push the air from this side, and you can watch the spring move. Okay. Yeah, you can see that the spring at one place squishes, and then it spreads apart. And sound waves travel through air just like that. And how do you make the sound wave? You wiggle something in the air that pushes on the air, and then you can see, and you can send this wave through air, and it travels until it reaches its final destination. Well, actually, the sound travels to the bottles too. And as it travels to the bottle, it makes its way through the neck. Then it travels down, bounces from the bottom, and travels back up. The parts where the string was squished, these are called notes, and the parts where the string was spread apart are called antinodes. Well, when the note, or the wave itself, reaches the bottle and enters the bottle, the pressure slightly rises in that bottle. Then the wave travels through the bottle, bounces from the bottom, and travels back up. And when the wave leaves the bottle, the pressure lowers again. But this flask is different from this bottle, but it doesn't matter, because even this bottle can be used for the experiment I've shown you before. But we need to find the natural frequency on which this bottle will resonate. Well, the resonance is enhancing of typical frequency for some object. Like every object has its natural frequency. Well, how to find out natural frequency of this bottle? We can blow it. So here I come. Wish me luck. Yeah, it's like ship leaving its port. But I have a different bottle here, which is slightly larger, and I can blow even this. And as you could probably guess, the sound was different. And every bottle has a different sound, and the sound differs by three things. The first is an area of the neck. The second one is the length of the neck. And the third one, which is, like most of you probably guessed, is the volume of the container, volume of the bottle, which changes the sound. The larger the container, the deeper the sound, the lower the frequency of the sound will be. Well, I told you that when sound wave gets into the bottle, the pressure slightly rises, and when the sound wave leaves the bottle, the pressure slightly lowers. Well, the frequency in which this happens is around 100 to 200 times per second. So I can't do it with my hands. That's why I had to blow it. And these flasks from the beginning that were rotating have the natural frequency of 121 hertz. And with that frequency, I can make them rotate. And how? Well, I can fill the space in which the bottles are with their natural frequency, which will cause them to resonate. Well, this is called Helmholtz resonance. When the bottle starts to vibrate, the walls are starting to vibrate, and they are pressing out or pushing out the air and then sucking it in, and then pressing out, then sucking it in, and pressing out and sucking it in, etc., etc., etc. And they're doing it really fast. But if that was the reason for movement, well, it wouldn't move if the air was leaving the bottle like in a line. We could have a laminar flow. We don't have the laminar flow here. The air leaving the bottle creates vortices in close proximity to the neck, and they're best shown by a video that we pre-recorded before. So I will ask well, if there was a laminar flow, the smoke would leave the bottle and would continue in a line from this bottle. But because of that there is not a laminar flow, and there are vortices that you could see on the video, the air leaving the bottle, like the next wave that comes, will push from these vortices and travel back to the bottle. And this wave, this sound wave, takes with itself a momentum which can give the momentum to the bottle and set it on its trajectory forward. So push by a push, 121 times per second, the bottle starts to rotate in direction from the neck. And the thing with the natural frequency, I can show you that not every frequency works. I will change the frequency that I'm playing from the speaker right now, and I will show you that the bottles won't move until I get back to their natural frequency. I'll take some time to stop the rotation, so you can trust me that I'm not moving it. So the D is not the right answer for my question. Okay, so now they're pretty still. And I will play 200 hertz, okay? Nothing happens because I didn't choose the natural frequency of the bottles. If I change it back to those 121 hertz, just give me a second. I'm there now. And I totally ruined my credibility by moving those bottles right before the experiment. But I hope you can still believe me that it wasn't me rotating these flasks. And I was telling you that it is DIY experiment. You can find at home easily two same bottles by blowing into them, finding their natural frequency. Using your phone, you can find the app on the App Store or anything. And measure the frequency. Then possibly you have at home some kind of speaker studio sound system which has a subwoofer. You don't have to have this kind of speaker. You just need the small one which makes the low frequencies, and then play the natural frequency of these bottles and impress your friends. Okay, so this is how you can move stuff with sound.
Thank you, David. It's a very interesting experiment, a loud one, as I can say. And I love that this is an experiment that we can try at home. And I was wondering, just a quick question. Would it work with glass bottles?
I don't think so, because the rotation starts when the bottles start to vibrate. And the walls of these bottles have to vibrate in such a way that they're pushing air out and in. So the glass bottles, it could work, but it would take a long time for them to press enough air out of them. Okay, and I actually forgot to see the answers for my question, so I'm sorry, but we can see if you guessed it right. So the Kakarinka says C, yes, it was the air flowing from the bottles. Another correct answer, C. Tobias Loquens, B, I think it was, wait, I don't remember the, I don't remember air from the bottles, was the B, yeah, sorry. So the B and C are both kind of correct. The B is really the best you can say, because it started rotating after the air was pushed out from these bottles.
Okay, so thank you very much, David. I think it's all. We have 2 experiments, 2 performances behind us, and we are ready for the next one. And our next performer is Anya. Welcome back, Anya.
Thank you. It's good to be back.
Yeah, thank you for coming. And Anya, or should I say Dr. Anya? I'm not sure what would you prefer. But I believe...
I'm still not used to Dr. Anya, so just keep it Anya.
Okay, I will keep it Anya then. Okay, so you finished your PhD studies, as hopefully people got from my little joke, and you still work at CERN preparing science shows for the new science center that will hopefully open later this year. Is that correct?
Fingers crossed, but for now it looks like it's going to be opening in the fall. Yes.
Yeah, and how are the preparations going?
It's interesting. It's interesting. It's going somewhere. The exhibitions are already installed almost, but everything else still needs a bit of time to get installed. So hopefully we'll be able to go into the building somewhere in the summer.
Okay, and what about your science shows? How many science shows are you preparing?
Well, several. Currently we have 4. So 4 are already performed in the biggest icon of CERN, which is the globe. But yeah, we're thinking of preparing 2 more until the opening.
Okay, perfect. And as it is already our little tradition with the first 2 performers, we also have a photo from your Instagram, I guess. And I would like to comment a little bit on where this is, why are you there, and why do you seem so excited about being there?
Yeah, this was actually the reason why I was excited is because, judging from the mask, this was somewhere last year when we just were able to come back on site to go and see stuff again. And this was me in front of one of the experiments at CERN. So basically 100 meters underground. And it's just such a fantastic thing to see. I've seen all of them several times already, but still every time you go and marvel at that just almost a miracle of technology. It's really, really, really glorious. It's kind
I
of
could imagine.
incredible to see what humankind is capable of.
Okay, thank you for commenting on that. And Anya, are you ready for your presentation?
I am trying to refresh my camera on my phone because it doesn't want to connect to the stream, but I can start talking beforehand. I have the experiment
Okay, then.
only ready for the last, so by then I can still talk a bit, and I won't be as long as some of the others, just to give more time to. Well, I assume Michael is gonna need a bit more time after me.
Okay, great. Thank you, Anya. Okay, so then the stage is yours, and you can start talking.
Perfect. I apologize to everyone because I'm gonna every now and then look at my phone and try to click the link for having it join the studio. But meantime, what I want to introduce is, well, a very, very difficult topic. So at CERN is the world's largest particle physics laboratory. And here we're trying to explore the biggest mysteries of, well, basically humankind and of the universe itself. So one of the things that we're always wondering is, where did we come from? So how did the universe evolve? How did all of these things happen? Which of course continues into, what are we made of? And then the last question, for some maybe even the most interesting one, where are we going? So what's going to happen in the future? Well, not just years, but millions of years, billions of years, trillions of years with the universe. So in order for us to be able to learn that, we need to be discovering, well, invisible. We have to discover invisible parts of our universe in order for us to be able to understand it. And of course, in the experiments such as that one that you saw in my back to the past picture, we're trying to both study the particles that we already know and discover something new. And I think one of the most famous things about CERN, other than a gazillion of different misconceptions and theories, conspiracy theories, is, of course, a famous movie in which Tom Hanks saves Vatican, called Angels and Demons. I don't want to advertise this movie or the book too much, but the storyline that we have there gives us some good hooks for which we can about which we can discuss. So basically, the story is, there's a bad guy coming to CERN, stealing something called antimatter, going to Vatican and trying to blow it up. There's many non-truths in that book, but one of the truths is that we do in fact produce something that's called antimatter. What is antimatter exactly? So antimatter is basically just the same kind of thing as we're made of. We're made out of matter, just that all of that has a different charge. So it has the opposite electric charge. For example, if we look at an atom has protons, neutrons, electrons, and let's say electrons, they have negative electric charge. Anti-electron would then be the same kind of thing as electron, but it would have the different charge, so a positive electric charge. This particle would then be called a positron, and positrons are antimatter. We already know something about positrons since middle of 20th century, but what we don't know is, well, I'm going to ask you. I'm going to use my question now just to hint it. Antimatter was supposed to appear in the universe a few fractions of a second after it was made. So basically at the time of Big Bang, we would have equal numbers, well, equal amount of matter and antimatter. Yet everywhere we see in the visible universe and even invisible universe, we only see matter. we don't really see much of antimatter. So the question for you would be, so why is universe composed largely out of matter and not 50-50 matter-antimatter mixture, if, of course, we say that that is how the universe came to be, that we had a 50-50% of matter-antimatter mixture. So this is something I'm going to let you dwell on a bit while I continue my trying to connect to the stream and talking about an experiment. So antimatter can be considered very difficult to catch and very difficult to hold. That's for the simple reason that whenever antimatter particles would meet with their matter particles, so let's say anti-electron would meet with an electron, they would do something called annihilation. What is annihilation? Well, annihilation is Einstein's most famous equation coming to life, meaning whatever the mass of those particles is, it's gonna go into full energy. So they're gonna completely disappear into basically a blast of energy, which is really, really interesting, but it makes research really difficult because we can't hold those things. So one of the ideas that a very famous physicist, Wolfgang Paul, discovered is a quadruple ion trap. So quadruple ion trap is then the reason why I chose this experiment to present in this stream. What we use in this quadruple ion trap is electricity. We use alternating current, which we enhance quite a lot and then send into a specific device called a Paul trap. So I will take this device slightly closer now that I don't have the second camera. So this is a Paul trap. This is something that we have actually made ourselves in our laboratories, not the scientific one, the educational ones. So what we have is a 3D printed box, and here at the very center, what we have is 2 electrodes. They're actually really weird electrodes. Typically, when we think about electrodes, we would have an image of 2 different antennas or something like that. Well, here we don't have antennas, the normal ones. What we have is a circular antenna, and of course, on the bottom, a tiny, tiny little button antenna. So these 2 are then connected to very high voltage that is alternating. So what we create with this is a changing electric field. Actually, it's vibrating electric field. And why is this useful? What we know from electricity is that positive and negative attract, and positive repel. Therefore, if we want to catch something, let's say, positive, we would, of course, maybe be able to levitate it above the positive, but that would require a lot of space and everything. So it would very quickly just run off and meet another negative thing somewhere else. Or what we could do here is basically juggle. So this Paul trap is basically juggling using electric field and holding our charged particles together. It's slightly difficult to understand, but the phenomenon is really, really, really cool. Today, for catching these particles, I'm unfortunately not using antimatter because that wouldn't be at all visible on screen. And at the same time, we don't really have a lot of it. What I will be using is lycopodium. So lycopodium or lycopodium, depends on which accent you want to use. It's basically a dust. It's like white dust that comes from spores of some plants. So this is actually a biological substance that, because it's such a tiny dust and because of its properties, when we shake it like this, due to friction, it becomes charged. So it becomes a charged particle, and we can use it in our experiment. And now I'm going to try one last time if I can connect my phone, because only with the phone I can really focus well on the experiment. And then we can see what it actually does. Yeah, this is not working. It was working before, but now it kind of stopped. And let's see if we can still see it with the other camera.
Yeah, Anya, like these things happen. We are live, so no worries about it. But may I suggest that we may continue with Michael's performance and try to figure things out in the backstage and get back to you when the second camera works? Would that be better for you?
First thing that I'm going to try is retry a second camera that I have.
Yeah,
and if that one
still
works,
something that, yeah, if there's still something that you want to try, then let's do it.
Because this one I can do while I'm on the camera. Yeah, I don't think it's going to work.
Yeah, we hear some beeps.
Yeah, you can hear the beeps of the GoPro, but
Yeah.
you can't see what the GoPro is showing for some
Unfortunately.
reason. So yeah, I would then say maybe we continue with Michael. But one thing that I can do in the meantime is, of course, answer the question or see what the answers to the questions were.
Yeah, let's do
because
that.
otherwise people are going to get nervous.
Yeah, definitely. Let's do that.
So there were 3 answers. The first one came from Adam, saying no idea. The second one came from Yotuch, because we're unable to find it. And the LH said antimatter can recombine into matter. I will unfortunately here have to go with Adam's answer, because no one has any idea. So we have no idea why everything is made out of matter, and we don't find any antimatter. But studies that we have and detectors that we have, even in space, they're showing that there is no antiparticles, at least not as many as we would expect if there would be antimatter hidden somewhere in the universe. So even though we would be able to find it, there just isn't any proof of it happening. So I was looking forward to someone saying a completely new answer that we haven't tried out or researched yet, but unfortunately, no, none of you gets a Nobel Prize.
Yeah.
But maybe
Okay.
better luck next time.
Not today.
Now
but
I go
maybe next
try
time.
my camera.
Okay, so we will do some work in the background, and until we're finished, we can see what Michael has prepared for us. Welcome back, Michael.
Hello, it's great to be back on Science On. Thanks for having me.
Yeah, great to have you. And it's been a year since you've been here last time, and I heard that you had an eventful year, didn't you? And I think you've quit your full-time teaching job to make a full-length science show that you are touring with in 3 different languages. And yeah, is that correct? Is this what you're up to in Spain as well?
Exactly. And in Spain, it's actually, I'm splitting my time between doing science shows and walking across the country. And with this small bag here that fits in my backpack and doesn't weigh much, just did 3 science shows in Burgos at the end of last week. So it shows you don't really need much materials. But yeah, that's exactly right. After 15 years of classroom teaching, I finally had the courage to make my own science show and try and tour it around more or less full time. There's a lot of other things I'm doing at the same time as well. But since June, I've been to 14 different countries in 4 different continents, performing, like you said, in 3 different languages.
Mm-hmm. Okay, and as it was the case with other performers, we also did some research and found some photos of you, and it might be connected to the tour, but you can comment on that. So can I have the question? sorry, the picture. And can I get an answer from you? What is this picture about?
Okay, so that's an experiment, and I can actually show that experiment if you want, although it's not directly related to vibration. But it uses this tube that I have with me right now. But I was in Morocco. That was mid-February or so. And I was biking through Morocco, Mauritania, and Senegal, doing shows and running workshops for teachers. And this was in a town, I hadn't contacted them ahead of time. I showed up at the police station the night before, asking if there was somewhere where I could camp. And after sitting around for a while, there was a lady who came in and they said, oh, you can stay at her house. Invited to her house, and as we started talking, I explained I'm a science teacher. I propose free science shows everywhere I go. Did she know anyone at the local school? And she said, yeah, we can go there before you leave tomorrow morning. Let's go there. School starts at, I forget if it was 8 or 9. I think it was 8. So we show up in front of the school, and no teachers have shown up on time. So the school's not open. There's no teachers, no administrators, but kids are waiting outside to start school. So eventually we say, let's stop waiting. Why not just do a couple experiments here in the streets for the kids that are waiting for the teachers and administrators who are late to start school? And there, so the 3 languages I performed in are English, French, and Spanish. Their officials and like people who've done university speak French. The level at a school in a village isn't that high. So I needed to pick experiments that were very visual, and they didn't need to be able to follow my level of French that well. And it was okay if they couldn't hear it so well with the crowd. So that was why that was one of the ones I ended up choosing there, to do any very noisy, not language friendly, like not a lot of common vocabulary context. That still worked well, although I don't think it'd be worth trying to test the students on anything I showed that day.
Yeah, okay. Thanks for a very interesting story from Morocco. And I suggest we leave the experiment for the discussion later.
Perfect. Okay? Yeah, and I'll get on with the experiments that I plan to show you, right?
Perfect. Thank you very much. The stage is yours now.
Oh, thank you. And of course, when I was watching some of the other performers, I got a lot of great ideas, starting right off the bat with Stuart with elastic bands. So while waiting to go on, I actually made my own version of his tin can and rubber band one. And as I mentioned, I'm on the road, so this is actually a water bottle I was intending on drinking water out of tomorrow. So my girlfriend who I'm walking with might be annoyed that we now can't drink water on the road until we find another bottle. But I just wanted to show one effect that starts off kind of as an illusion. So same thing with Stuart, right? We've got the rubber band making a noise. But what I'm going to do now is I'm going to grab it in such a way that when I stretch it, the pitch is actually going down. Hopefully that's coming through on the audio. But of course, I haven't broken science. It's not an exception to what Stuart did. It's just the illusion of taking extra elastic bands. So I let that slide through as I stretch it, which allows the pitch to go longer because it's a longer bit of elastic band that's stretching. But if I just stretch it without letting that go, it will be the same pitch, longer or shorter. And that's a great lead-in to the first thing I was actually planning on showing, which is like a 2-dimensional rubber band. So you can see I have rubber band and 2-dimensional rubber band of the same color. It's actually a balloon, but it's made of a similar material. And as I stretch it, instead of the elastic stretching in 1 dimension, only its length is changing, now it's stretching in 2 dimensions. It's becoming a bigger sphere. And you'll notice that if I vibrate my fingers off the surface of the balloon, I make a wonderful, beautiful sound there. I'm sure anyone else who can hear that is just loving the sound of this. But my question is very similar to Stuart's question. If I inflate this balloon more, so if I add more air and it gets bigger, will the pitch get higher, lower, or stay the same? And as you're answering that, remember, with Stuart's example, as we stretch it, the pitch will stay the same. So think of what happens when I stretch the balloon, which is now in 2 dimensions, and I'm having it vibrate. And you've now had a little bit of time to answer. So now I'm going to start showing with a small amount of air, and listen closely to the pitch. A bit more air. Yet more. And I think that should be clear that the pitch is going up as I add more air to it. So contrary to the one-dimensional case of the rubber band, with the two-dimensional case, the pitch is actually going up as it's stretched more. And the reasoning behind this is a little bit more complicated, but as it stretches, not only is it stretched tighter, but it's getting thinner. You can see that with the color, like when it's not inflated, it appears fairly red or a very light pink. The more I inflate it, the lighter it gets, because it's being stretched thinner and thinner. And so when it's thin enough, there's a lot less mass per unit area, and so it can move back and forth a lot quicker because it's been stretched in 2 dimensions, not just one, so it gets thinner at the square of the rate. It's with 2 different phones with 3 frequency generators. Same frequency, similar volume. And now if I turn them both on, and I'll hold them on camera so we can see them together, there will be certain distances as I bring them further apart that will appear a bit quieter and a bit louder. Here's a quieter spot, and then once they get a bit further away, the sound gets louder again. And this is exactly what Stuart showed a little bit more clearly, turning off the lights and visualizing sound, the phenomenon of interference. And if I move them back and forth a little bit quicker, you can hear as we go through the different frequencies. But one of the complications of this is I'm moving my hands in 2 dimensions. I've planned it, I'm moving them both the same way. I can move one further away from me. We hear it's similar as well, but a 2-dimensional interference pattern is much more complicated than a 1-dimensional interference pattern. So I'm going to cut out one of the dimensions. So just like with elastic bands, I was adding a dimension before. Now I'm reducing a dimension. And here's where the toilet paper comes in. And to focus on the toilet paper, you'll see I have a beautiful notebook that was given to me by Vita Science Center last time I was there. So as we mentioned, I've traveled around a number of places looking for experiments. I actually biked to Vita from Switzerland last year, and it was wonderful to meet people in person and spend time there doing a pocket science workshop. Now my headphones are all tangled up, but the Vita notebook showcased here, and it's actually where I was taking notes while the others were performing, because I'm always looking for new ideas. Now I've tangled up all of my headphones again. Okay, so now getting back to the frequency generator, plugging in headphones, turning the volume up to the max, because headphones are kind of small. And when I turn up the frequency to a frequency that headphones can work pretty well at, then we should be able to hear that. And I'm going to go to near the maximum volume we can get with headphones, which is around 6,000 hertz. And I'm going to pick 6,000 right on the dot. So it's going to be like a pretty even number. Oh, and actually, just before I do this experiment, another question to ask everyone. It's how fast approximately do you think the speed of sound is? And I think when we pull up the question, I gave 4 choices to choose from. So it's not just like anything. So if we can pull up that question, what do you think the speed of sound is? And indirectly with this experiment, we'll get to a calculation of the speed of sound. So we'll get back to your guesses at the end of this experiment. But because it sometimes takes a while for your guesses to get all the way to me in Spain, because I'm a little far away and in the basement of a pilgrim's hostel that doesn't have an ideally good internet connection, we should have the answers by the time this experiment is done. So getting back to the experimental setup, 2 headphones that are both working, making a pure frequency of sound at 6,000 hertz. And here I'm just going to lower and raise the headphones in the tube of toilet paper. And listen closely to what we hear. And hopefully the microphone is picking it up well enough that you should be able to hear here. It's quite loud. And here we get to a point where it's quieter. And then another point where it's loud. And then another point where it's quieter. And these are nodes of constructive and destructive interference. Where it's louder, that's where the 2 sound waves from the 2 different headphones are meeting together at once. Because these are cheap headphones, and because the frequencies generator has no need to produce a stereo sound, when they're right at the bottom and they're in the same position, or a very close position, that will be a node of constructive interference because both headphones are making the same sound at the same time. As I raise it up, once they're separated by half a wavelength of sound, we'll get a node of destructive interference because when there's a high pressure zone from the low one, from like the one that's positioned lower, that corresponds to when there's a low pressure from the headphone that's higher. That is to say, we have a maximum and a minimum corresponding in the same spot as I move it up. If I move it up another half wavelength, then they're separated by exactly 1 wavelength, and then we'll hear constructive interference, where there's a high pressure zone that reaches the second headphone exactly when it's emitting the next set. And so we can use this, and I can pull the difference between the 2 to measure the wavelength of a sound and hold it in my hands. It's slightly easier to listen to where it's quieter, so let's go about there is about where it's quietest. I'm going to pinch that with my fingers and remember that distance. Here, constructive interference is going to go through that all the way to the next destructive interference. So here, in my hands, and I'm going to turn off that noise because it's a bit annoying. Here in my hands, I'm holding 1 wavelength of a sound of 6,000 hertz. So you can see 6,000 of those waves are being produced every second. We're just going to bring this to a measuring tape I brought in the foreground to measure about what that wavelength is. It's probably too small to pick up on camera, but that's just above 5 centimeters. Like if I hold it down, just shy of 5.5, like 5.4. But for ease of mental calculations, doing this on screen, let's round it to 5.5. So about 5.5 centimeters. So this frequency generator is making 6,000 waves that are 5.5 centimeters long each second. Well, I mean, the speaker is making the sound waves. The frequency generator is making the frequency, which gets the headphones to make the sound. Anyways, the sound, we're having 6,000 of these waves that are 5.5 centimeters each being emitted each second. So if we want to know what distance it traveled each second, then all we need to do is multiply 6,000 by 5.5. And the speed of sound, of course, then is 33,000 centimeters per second. And of course, everyone uses centimeters per second in their class. No, no one uses centimeters per second as a unit. That's a ridiculous unit. We'll divide by 100 to get meters per second. And it's about 330 meters per second, which is a reasonably good measure of the speed of sound. Those of you who guessed B, 330 meters per second, that's approximately the speed of sound. If you look it up, you'll often find values like 340, 335. It depends on temperature and pressure. It varies a fair bit. So anything between like 320 and 350 is pretty spot on. And that one, I actually learned from Science in Advent, which is a cool science advent calendar. And I really like that one because it uses a surprisingly simple thing to measure something that most teachers I've met have said, oh, you can't directly measure the speed of sound in class. Well, you can measure wavelength and indirectly get it. So it's pretty easy. So that's what I wanted to conclude with. It's been great being on, being able to share these experiments. Thank you again for the opportunity.
Thank you, Michael, for showing us these experiments. And I really loved, what I really loved about them is, first, that you can change the result of the experiment by adding or subtracting dimension, a spatial dimension, in the case of the rubber bands and balloon. And the second, that you can make such experiments even with things that everyone has on him or on her, even on track. So a phone, preferably two, a cheap pair of headphones, and toilet paper, and of course a Vida notebook, right, and a measuring tape. So maybe the last two.
Always the Vida notebook.
Yeah, sure. You have to write it down, right? It's not science if you don't write it down. Okay, thank you.
If you look through these pages, you'll be amazed at like all the different science communicators I've gotten inspiration from. So all thanks to Vida and the Vida notebook.
Yeah. So thanks for that advert. And I think we can continue. We have 4 or maybe 3.5 experiments, presentations behind us, and I think we are able to get back to Anya. Welcome back, Anya, again. So how's the second device behaving?
I think it's working. It
That
should
would
be
great.
working.
Yeah, we can see
yeah,
it.
it is. Fantastic. And actually, it's even better to see everything now because the room has gone dark in the last few minutes. So it's fantastic. So
Okay, great. So we're super excited. You did a great job at teasing this experiment. So
a long
we are waiting.
teaser, yeah. Okay, so what we're going to see now is when I turn the pole trap on. So just to recap what we did before is we have 2 electrodes. One is here and one is here. And in these 2 electrodes, we have alternating current. So that is already some oscillations going there. And these oscillations are going to help us put the lycopodium dust and have it just suspended mid-air. But of course, that doesn't work if the power supply is turned off. So let's put it back to 0 and turn it on. Okay, so power is now coming from the supply, for the power supply, going through the transformer and into pole trap. And of course, we need to make it stronger because nothing works if you don't have thousands of volts. Well, some things work without thousands of volts. Okay, so now we don't yet see anything. So what I need to do is I need to open the lycopodium. I will take it with a tiny stick, or actually a knife. So what we can see is, yeah, you can put the other camera on. What we can see is on knife we have some lycopodium, We're going to put it inside here. And you can see it suspended mid-air. And what you can see is that these things are actually jumping up and down because they're being juggled by the electromagnetic field. Currently, they kind of looks like we have lines, but actually all of these spores are actually very tiny dust particles. And why we see them as lines is because they're vibrating so fast that our eyes can't really detect that they're moving, and they just appear as lights. That's why we're going to do some other kind of oscillation, and we're going to go for something that interferes strongly with the oscillation of how the camera works. And we can now try to see if we can find the right frequency of the LED light oscillating, that we can see these dust particles dancing a bit better. And now you can really see them dance. We can even basically try to stop them. Now they're going faster. So what we're trying to do here is we're trying to catch the frequency at which these particles are moving up and down. And if we catch it just the right time, they're gonna appear still. Or at least almost still. So you can see that they're not really moving that much, even though everything else other than the light is still the same. So they're still technically dancing the same way, which we can see if I just increase the frequency at which this LED is blinking. And of course, it now looks like it's interfering with the camera a lot. But actually, this is caused by one effect that cameras have, which is that cameras also get the image in by scanning in front. So we basically have a scanner, a live scanner, and the scanning frequency can then, of course, be at a similar frequency that's what we see from the LED light. And if that happens, then we see those scanning lines going through our camera. That's also the reason why sometimes on the internet you find people making a photo of a dog and then the dog seems like it's super long. And that's just because the camera didn't catch the entire thing at the same time, but it basically closed the shutter from one way to another, and that's how it goes. So this experiment, the Paul trap, of course in a way fancier and bigger edition, is currently helping one of the coolest experiments at CERN do their research. That experiment is called G-bar, and G-bar actually means anti-gravity experiment, because what they're trying to see is if antimatter falls down or falls up. That's something we don't know yet, and we're hoping to see in the next few years. But yeah, that is it from me. So this is the great experiment that I was always preparing for. Luckily now it worked, and I'm looking forward to having some questions.
Yeah, I'm so astonished. This was one of the most beautiful experiments I've seen on stream, and I'm so glad that it went through so well. We could see a lot of, excluding the interference with the frame rate of the camera, but other than that, it was perfect. Thank you, and I'm so glad that we actually got to see it. And based on the time that we have, I would like to propose that we omit questions now and move further with experiments, and we will get back to them during the discussion session.
Awesome.
Is it
See
okay?
you then.
Perfect. See you later. First, before we start with other experiments, I would like to thank our audience for keeping up with us, for posting comments and answering questions. It's great. It keeps the interactivity of these streams. And yeah, it's what we are proud of, that we can keep these streams interactive and live. And right now, I have Adam here. Adam, welcome.
Hello. Hi.
And maybe you should be welcoming me because you're a core member of Science On. I'm just a guest host. Yeah. So, okay, thank you. And yeah, so I mean, you're a full-time teacher, right, at the grammar school?
Not a full-time, but part-time. Yeah.
Okay, part-time. Yeah. But you're a part-time teacher at the grammar school, and also one of your one thing that you're most passionate about is in science is radioactivity.
Yeah, radioactivity is awesome, yeah.
Yeah, and I think we have an evidence of that, or maybe a combination of that. Can I have the picture?
Sure.
Is this your passion for radioactivity and teaching at grammar school, or is it something else?
Yeah, this is combination of these things, because these two girls are my students, and the man in the middle, that's me, in an old army suit. Like anti-radioactive suit, we can say that like that. So it's suit which soldiers wear when there was like catastrophe like Chernobyl, for example. So this is like original. So that was the start of our theme, radioactive theme in school.
So what subject was this? Is it physics?
It's physics, yeah. It's physics.
Okay.
And the students are looking for the radioactive stones around our school, and they should put the mark to the maps where it is and measure that.
Okay. So it's kind of like a radioactive egg hunt, right? It was Easter a few weeks back.
Yeah, you can say it like that, yeah.
Okay, great. Thank you very much. I think we're prepared. You have some things here. I'm super excited to see what they do. And the stage is yours now.
All right, thank you. But it's not radioactive, yeah. So you can see our thing. But firstly, I have a question, because how can we make levitation? That's the question for us. We can use something like aeroplane, or paper plane, and use it for levitation, but it doesn't really levitate, it just moves, it flies away. So it's not really true levitation. We can use something like, I don't know, the superconductors, for example, but there is really low temperature for using this kind of levitation. So we can use electromagnetic levitation. That's also difficult, because you can use only few materials for this kind of levitation. But we have one levitation here, which is acoustic levitation. Because today we are talking about vibration, sound, and so on. So we can use sound for levitation. So this is our device. Is it all right? Yeah, is it all right? So now there is a high frequency to our speakers, or transducers, but it's basically a speaker. And we can put something in the middle, and it stands right there. So this little thing is levitating in the middle. There's no piece of string, anything. It's just one piece of styrofoam in the air. And now comes the question, how is it possible? Because this is not really, it's not something that you can find on the streets or on the bathroom, for example. I don't know. So we can use we can explain that, yeah. So sound is vibration, it's wave, and I need a hand or finger. David, I need a finger, your finger, David's finger, and we can show, yeah, here's finger, good. And if we have a wave, it's just some kind of this disturbance of some field or matter. So if I push this piece of string or rubber, I create wave, and this wave travels from my direction to David. Right? Yeah, it's like that. And there, it repel and travel in the other direction from David to me. And it's basically another source of waves. So if we combine these waves, we talk about interference, so we have some idea. So it creates some station waves. You can see it like that. But we can use something. Wait here. Wait. We can use something much more faster than my hand, like a jigsaw. Yeah, just pull it a little bit. Yeah. Oh, shit, that was too much. That was too much. All right, all right. And now we can see how our waves combine. There is the area with knots. There are stable points of our vibration, and there are also places where antinode is created, where it vibrates the most. So these two waves are combined and create some these patterns. Okay, thank you, David. That's nice of you. So big applause for David. Thank you very much. So, but this was a transverse wave. But the air, it's not really, the sound doesn't transfer like transverse wave. It is a longitude wave. So we can have a second animation. Here is the first animation. Second animation is here. So this is how sound is created, or how sound looks like in the air. And especially this is a standing wave. So we can see the spots where the particles of sound doesn't move. It sticks in one place. And this is the place where our styrofoam ball can hold where it is. It is a place where the node is. And there is a question for you, dear viewers. How many these styrofoam balls we can put inside our levitator? You can make a guess and tell us what you think. How many? There is one, but we can put more of that. And meanwhile, we can visualize our knot field, this weird thing, because we can visualize where the knots are located. Because in this setup, the knots are not really points or lines, it's like whole areas. So we are going to create a steam or gas. And now, if we put it higher, higher voltage to our power supply, yeah, we can see the places where the gas is more concentrated, and this is the places where the knots are. Yeah, like this. You can see like the lines. And this is the place with the knots. So it's kind of a nice thing, I think. Oh, it's beautiful, beautiful thing. It's charming, isn't it? It is. I think it is charming. So, do you have any guess? How many balls can we fit inside our thing? Three. Okay. All of them. I have a lot of balls. Yeah. That was a weird sentence. So we can try one. Here's one. You already see that, yeah? Here comes the second. Ah, it's vibrating. We put volume, voltage down a little bit. Yeah. So here's the second one. Here comes the third. Here comes the fourth. Sixth. Seventh, maybe. Yeah, it is there. So eighth. All right. 9. So maybe 10, but 9 was there stable. Now there is like six balls in our knots, in our acoustic levitator, and there's also one thing. It is in stable position, and even if we like turn it in 90 degrees, it's still in the stable position, so we can move it like we want, and it just stays in this place. So it's a really amazing thing, and this is also a DIY thing. You can create it your own. It's not that hard. You just need Arduino, one driver, and this thing, these little speakers, and you can buy it online. It's not that expensive. So that was it, but we must use only this light thing because we are limited in our levitator with size, density, mass. So we can use it only for light things. So thank you.
Wow, thank you, Adam, for another beautiful experiment. I mean, how long did you have to practice to be consistent with these? How many was it? 8 balls?
Was
or 9?
9. 9 was stable, and the 10th destroy all thing.
So you can do 10 in better days.
Yeah, I think 10 or maybe more.
Okay, great. So how much practice did it take?
Like the whole creation, the whole setup, or
no, just to
a
be able
training
to position the balls.
Like in half an hour, maybe an hour.
Okay, it's not that hard.
It wasn't that hard. Yeah.
Okay, great. Thank you very much. And yeah, you said the DIY, but you did. Oh, okay. So continuation of the experiment.
It's just you can talk.
You are disturbing the sound.
Yeah, a little bit.
Yeah, okay. And so you did not make the array. So the array is what has to be bought.
Yeah.
But the other things, the other stuff that we can maybe see how it is set up here. So no, we can't see it because it's behind it. Yeah, it doesn't matter. So yeah, you can buy some cheap stuff and make this, but this array. Okay, thank you very much. I think we've seen 5 performances, thankfully full ones. And I think we have a question from audience that we can have it here. So Adam, did you try anything more heavier? So
yeah, I wanted to try some liquid like water, colored water, but I didn't manage it, so I didn't try it. And also I wanted to try an ant, like the animal, the insect little, but it escapes. So
escapes from the levitation?
From the bottle.
Okay. So yeah, I thought that the ant didn't find it as exciting as you to be able to levitate. Okay, so thank you very much.
Yeah.
And we have another last experiment, and this one is special, so it will start right after the break. You will see why.
Hi, everybody. Chris and Diane here from the United States. We're really excited to be a part of today's program. Even though we can't be there in person, we hope you'll enjoy what we put together. Chris, We're talking about
Vibrations.
vibrations.
Yeah.
Boy, I can't think of anything fun to do with vibrations.
You can't? Are you kidding me?
You have some ideas?
Oh my God, we have so many things to show them.
Well, let's get right to it.
So what do we got going here, Chris?
Well, we have 4 metronomes, and at the moment, they're not doing much, Diane.
No, not doing much at all.
However, we can change that.
Okay, let's set them into motion. Okay, they're all like out of whack.
They're all out of step, aren't they? We say they're out of phase.
Oh.
But you know what?
What?
I have a feeling if we wait just a little while...
What's the big deal here, Chris?
Hang on.
Oh, 3 of them are together.
3 of them are in step, aren't they?
Yeah. But, okay, now those 3 are in step.
What about this guy?
I know.
Oh, they're
right,
all in
they're all in
step.
step.
They're all... You'll notice that the metronome has a definite frequency. That is the rate at which it swings back and forth. However, I can vary that by moving the metronome. If I have a second metronome on the same platform, which you'll notice moves, this metronome can affect the motion of this one through the coupling due to the platform. And very quickly, you'll see the 2 move in phase. If the platform were stationary, that would not happen.
Ground when you're on a swing or whatever, everything has a natural frequency. So like this ball, if I put it in motion, it'll naturally start oscillating, and that would be called its natural frequency. Okay? Now notice this ball, different length on this pendulum here with this ball. And so notice that's a much different natural frequency, right? And then this long guy here, I mean, he's got quite a different natural frequency. I mean, if you look at these 2 together, quite a different natural frequency. Maybe you've noticed this out on the playground sometime as you were on the...
So Diane, we have 4 pendulums, and they're all of different length.
Chris.
What?
I think they can see that definitely these 3 are of different lengths, but these 2, I don't know. They look pretty similar to me.
You're right, they are similar. So they will have the same natural frequency?
They should, yeah.
I wonder what that means in terms of all 4 pendulums. In other words, if we set this guy in motion, the others really don't respond.
Yeah, nothing going on.
And this one, the short one, which has a high frequency, has some effect on the other 2 tennis balls, but not all that much.
No, not that much at all. Notice the string, they're holding them all together.
That's important because the string couples or connects the 4 pendulums' motions.
Kind of like the metronomes.
Very similar.
Oh, okay. Great.
You know what we haven't done yet? It's set one of these in motion.
Oh, yeah. Big deal.
Well, it is a big deal because its motion really doesn't affect the other 2 pendulums, but it sets this one in motion.
Wow.
When 2 objects have the same natural frequency, we say that a condition of resonance exists. And when resonance exists, energy can be transferred very efficiently from one pendulum to the other.
Well, that one stopped.
It is. But wait, now it's set in motion again. You see that?
Oh, wow. So this guy's...
eventually will stop. There it goes. And this one is moving with a very large swing.
Wow.
And back and forth it'll go because of the resonance condition.
Awesome.
Examples of resonance are very common. What we have here are 2 tuning forks that appear to be identical. Let's see if they produce the same sound. They do. They have the same natural frequency of vibration. I wonder what will happen if we strike one tuning fork and allow it to vibrate. how will it affect the other tuning fork?
And we interrupt the video with the live version of Chris coming in. So thanks for joining. We will have the question posted so audience can answer it in the comments in the meantime. And I would like to welcome Chris again to the stream, to the live stream. And I would like to ask some questions. And one of them would be that you mentioned that you want to visit Znanstival this year, again, which is a science festival, science street festival in Ljubljana, the capital of Slovenia. And I was just wondering what it is that makes it worth for you to travel all the way to Slovenia to be at Znanstival.
Well, I think it's such a wonderful festival. And the people there, such as the people on your program, are so much fun, and I learn so much from them. And can't forget the people of Slovenia, probably the best audience I've ever worked in front of. So all those things together make it worth the trip.
Yeah, sure. Okay. And maybe I would ask now the studio if we have some answers for that. And we will be seeing that. Now, D and, sorry, yeah, I can't remember what was the...
Oh, yeah, B and D. Let's see.
B and D. And another B. So what do you think how our audience did? Did they do good? So did they answer correctly? We will see in the video, right?
The second tuning fork will begin to move because it has the same natural frequency. Absolutely.
Okay, let's see it. Let's see it in the video.
So Chris, the sad thing about not being live is that we won't know what they answered. So we'll just have to show them.
Yeah, let's do that.
Okay.
So I'm going to strike one of the tuning forks.
Okay.
And let's wait a moment and see what happens.
Okay. Oh, you stopped that one on the right.
But this one is now vibrating.
Can you hear it? Stop it. And then, yeah. Did you hear it stop?
Yeah. It was definitely vibrating.
It was definitely
So
vibrating.
energy was transferred from this tuning fork to this tuning fork because the two are in resonance.
Even things like this fan have a natural frequency. And even a string has a natural frequency. If you remember, the pendulum, the length of the string made a difference as to the natural frequency of those pendulums. Now, let's take a look at what happens when we get the natural frequency of this fan to match or be a multiple of the natural frequency of the string. Oh, there it is. There it is. We get something called a standing wave. This wave's called a standing wave because it doesn't appear to propagate, doesn't appear to move down the string. It just looks like it's stationary with the middle part just bouncing back and forth. What do we call that middle part, Chris?
An antinode.
And the parts that don't move at all?
Like where my fingers are located?
Yes.
A node.
A node. Could you maybe try and get 2 antinodes?
Well, let's see. Ooh, ooh, ooh.
Oh, almost. There we go. There we go.
Whoa.
Aha! Do you
Whoa.
see it? So we have a node here, and we have an antinode here, and an antinode here, a node down here, and a node up where Chris's fingers are. This is called a standing wave.
Just like strings, metal plates have natural frequencies at which they vibrate. To show that, I'm going to place some sand on the plate. And now I'm going to try to excite the plate at its natural frequency.
Chris, are we looking for standing waves here?
You know what? These are two-dimensional standing waves. Just like with a string, there's a vibration that goes in this direction, and also in this direction. And what happens is those vibrations interfere, producing a pattern of nodes and antinodes, just like the string.
How will we know where the nodes are?
The node should be located where the plate is not moving.
Ah,
And
just like the string.
Just like the string. Let's give it a whirl.
Okay.
Now I'm going to adjust the frequency.
Oh, you can see it moving.
We're going to try to match the natural frequency of the plate.
Oh.
Really close, Diane.
Really close.
Now, oh, this is beautiful. Notice where the sand is dancing up and down. Those are the antinodes.
Right.
And what happens, this is terrific, what happens is the particles will move until they land on a node.
Right, because it doesn't get bounced around there.
It no longer bounces around at those points. And look at this pattern. Isn't that beautiful?
It is beautiful.
Look at that.
And it also got louder. Did you notice that when
Did
it was
really?
resonating?
Yes,
Oh,
yes.
yeah.
When we hit the resonant frequency, the plate vibrated more and the sound got louder.
That's beautiful, Chris.
Can we try to find one more?
Sure, go for it.
Oh, look at that.
Look at that. That's beautiful.
Oh, let's just let it go. Diane, look at that.
That's gorgeous. Look at those nodes. Nice nodes, Chris.
Nice nodes. Here, here, here.
Yep.
What a gorgeous pattern. Diane, we have a rather unusual device right here. This is called an acoustic levitator, and it consists of two ultrasonic transducers or speakers, one here and one here. The purpose of these speakers is to set up an acoustic standing wave. And just as you've seen, standing waves are characterized by nodes and antinodes. Here, you can't see them, but we have nodes and antinodes between the two transducers. Now, we're going to try something. I have a very small piece of styrofoam on the end of this little spatula. And what I'm going to try to do is place it at a node where there's no motion. The object is to get it suspended between two antinodes.
Oh, wow.
There it is.
There it is.
So that little piece of styrofoam now identifies a node.
Right, right.
Let's see if we can get two.
No.
What do you mean no?
I don't know.
Keep the faith.
Node. Come
Node.
on, baby. Come on, baby. Oh, yes. Yes.
Whoa.
Nice job. Wow.
I know. All right, so now it gets tricky.
Okay.
Okay, I'm going to try to suspend one more.
Just one.
Just one piece of styrofoam, and we may not be able to do it.
Oh, yes! Nice. So each of those pieces of styrofoam is located at a node.
That is correct.
And then in between there'd be antinodes, and that's why it couldn't stay there, because there was too much action.
That is absolutely correct. Now,
okay, come on. Come on,
we
could
may
you
have,
do one more?
Wait. We may have to cut the video right now, now that we have success. But why?
Why?
Let's go for 4.
Go, come on. Go for 4. That's pretty good.
Yeah, we may have to.
We may just have to be satisfied.
Because otherwise, yeah.
Oh, there we go. Woohoo!
Now.
4.
Well, that's it for us today. We hope you've enjoyed watching this as much as we enjoyed making it for you.
We hope you found the wonderful world of vibrations, standing waves, and levitation interesting.
Bye-bye.
Bye.
And that's it. The remaining part of the video from Diane and Chris wraps up our first part of the stream, which were the experiments. And now we move on to the next part, which is the discussion session. I would like to encourage all of you that are watching you have the unique opportunity to interact with our guests. You can ask questions. You can pinpoint the experiments that were most exciting for you and you want to hear more about, or you can just comment on what you liked, what you didn't like. It's up to you. You can take this opportunity and interact through the comments in all platforms that you are watching this stream on. So let's go to the discussion. And with everyone on stage, Chris, Anya, Stuart, and Michael online, and David and Adam here with me, we can start the discussion session. And I would like to start with Chris. And if we were following, we had some difficulties with connections, with sounds, and all this stuff. And I wanted to ask you, you said, or maybe it was Diane that said, that you are enjoying making the video. And I wanted to ask, were there any difficulties and challenges that you did not expect that came up during the shooting of the video?
Yeah, the advantage of doing a video is you can have all sorts of problems and the audience will never see them. And yes, we had problems with the sound level. For example, the tuning forks weren't as loud as we'd hoped. Getting the styrofoam particles to levitate, to get all four of them, was a challenge, as the sign said, a few hours later. So yeah, but it's a real advantage to be able to make mistakes and then edit them out.
Yeah, understand. And yeah, that's maybe comforting for Anya and Michael that we will do some editing magic for audiences that will see the edited version of this stream afterwards. So you can share the experiments in the full length in one piece. Okay, moving on, we have some questions from our audience. So I would like to ask the studio to show them on screen. And the first question is to Stuart. What was the most difficult physical experiment in your career of popularization of science? And did it work?
Great question. I don't tend to catalog things quite that way, but one which I'll use as the answer to that was one that actually relates in some ways to the experiment that David shared with the resonating bottles. There's a series of phenomena that's going on with that demonstration. And if anyone's familiar with those old little steamboats called putt-putt boats in English, you put a small little candle in a boat, has a coil of copper that goes around, one in, around, and back out, and it boils the water and it starts running along, but it ends up sucking water in one tube and then blowing it back out, and it runs along. And when you start to think about it, it becomes a little tricky. How's it doing that? If it's sucking in, then that energy should pull the boat in the opposite direction. When it blows out, the boat moves away. So why doesn't the boat just oscillate back and forwards? And some friends and I were investigating these sorts of things, and I remembered seeing water sprinklers here in Australia. You put water in to water the garden, the sprinkler spins around. The water comes out like a jet, and the sprinkler spins around. And so I asked the question, what would happen if you sucked water in to the sprinkler? Would it spin in the opposite direction? And we started doing a whole series of investigations about that, and only later discovered that this was a problem that Richard Feynman also identified. And we don't really have a great answer to it. We've got lots of people looking at it. So to answer that question, one of the things which I did And the experiment works. We're just struggling with a good explanation. So I put together a little tank with a jet down the bottom and a pump and a load cell to measure the force. And sure enough, when you squirt water out, not surprisingly, you get a lot of force. When you suck water in, same amount of water going in the opposite direction, nothing. So we're still trying to work out what the good explanation for it is. And these are serious scientists that I've been working with going, what's going on? So I love to find these kind of simple observations that really challenge your assumptions about what you understand. So that for me was a nice experience, even though we haven't kind of scratched the itch yet. So that would be my answer to that question.
Mm-hmm. Yeah, I think I understand. And what I found inspirational on this is that you can get like science progress just by asking questions that come up while experimenting with this, even in educational settings, even in entertainment settings. So it's great that these questions come up and get back to science. And I think we have another question from audience, this time to Michael. And the question is, what's your favorite subject from your backpack for experiments when you're on your science popularization journeys? It's your favorite object, subject, yeah, something like
that. That's a great question. I saw it pop up when I was presenting. So I actually prepared one of my favorite ones, which is one of my favorite ones to pull out of my back. I mean, there's a lot of different ways to answer the question. And my favorite thing is to use simple things that people could find anywhere and lower access barriers. My other favorite thing is using locally available materials, or like something that shows where I am. So this one, I did a version at the University of Burgos using like pens from the University of Burgos and a folder they'd given out, like Universidad de Burgos. And this is one of my favorite experiments that I did with that, because it's the other like favorite thing, which is to use an element that looks like magic. And this actually related to one of Chris and Diane's last experiments. And can I get one of the other people who's on this to be my volunteer to help me out with it? Oh, actually, I showed this to Last Science On. This is just like another version of it, but still, someone pick one of these 3 pens. No? No one can pick it? Did my connection drop?
It's good. Yeah. Oh, okay. I can be heard. So, what was the question? I should just pick one of these 3 pens?
Yeah, pick like the short, the middle, or the long. Oh, and fun fact, the middle pen comes from Slovenia, from the gymnasium in Celje, which Anya can remind us, is that her high school, or did I pick the wrong pen that I'm traveling with? Because I visited her high school in the fall and did a science show there.
Yeah, exactly. It's mine.
Excellent. So with your high school's logo, that's the pen I wrote the notes from today's show on.
Okay, that's great. So let's go with that one. So you promoted it well.
With that one. So I want you all the way from the Czech Republic, all the way from Brno, to concentrate on that pen and try with the power of your thought to get it moving back and forth. Ideally without moving the other ones very much. And hopefully that comes through on camera, right?
Yeah, it does.
And
perfect.
So that, I like starting with that one because it appears as magic, or it appears as telepathy, but then you can explain it with resonance, because I'm actually swinging the rod with the resonant frequency. Now that I'm swinging it a lot, it's hard to get just that one moving, but I'm swinging it with the resonant frequency, just like the pendulums that were coupled that Chris and Diane showed. So that's one of my favorite ones to use, incorporating things like Anya's high school and the University of Burgos. And usually I have something better, like up until I left Burgos, I was using a ruler and it didn't fit my backpack. So I got rid of it and I made this out of straws that I'm still traveling with. Hopefully that answers that question.
I bet it does. I mean, you're a great storyteller, Michael, and it's fascinating that you can put stories in those experiments in places that no one would expect, like a logo on a pen. So that's great. And I think we can go to another experiment that was exciting for our audience, and it was the acoustic levitation. And I think we have some question on that. So is it possible to make levitate a person by this ultrasonic speaker if you do not count the destruction of hearing? Yeah, okay, we don't care about the health, just the physics. So maybe I will ask Adam if you can comment on that.
Definitely not with this type of this setup here. But I'm afraid that it's not possible, not according our knowledge and our practical things what we already built, because the nodes and the antinodes are really close together. So you can't really put that large object as the person is into the this little spot or this little area. So it's not in it wouldn't be in a stable position. So it's not really possible.
But would you be torn apart? Or what would happen actually to you, apart from your eardrums being torn apart?
Not sure. Maybe if you have like really strong sound system, okay. maybe.
Okay, but getting back to more physics question, I have one which is still in this area, in the levitation. We saw a few examples of stationary waves, and we also talked about dimensions, spatial dimensions. And I wanted to ask, we saw a one-dimensional stationary wave, then two-dimensional on the plate that was in the Chris and Diane's video. And is this acoustic levitation that we saw with this array of speakers an example of a three-dimensional stationary wave?
Yeah, it is.
Okay, and in that case, why were the styrofoam balls all in one line? Are there nodes outside of this line?
Yeah, as we showed with a gas or with a steam, there is like the whole areas of the node, but the center part is like the more stable. So it goes like in there. Place. In that place.
Okay,
that
makes sense.
One little point.
Yeah, I guess we saw that with.
Because the area is like the biggest from that all parts, so it doesn't interfere with the parts where there is no node area.
Yeah. Okay, thank you for explaining that. And I think we have another question from the audience.
Yes, that's my question, actually.
Oh, it's your question.
Me.
Okay, so.
And I have a question for Anya, because you told us that when antimatter and matter collides, it like dissipates into energy, just pure energy. Is there any observation, or is that just a proposal that it should like turn into energy?
Yeah. So actually, when I say that it turns into energy, typically it goes into photons. So yeah, there's been many observations, and this is one of the ways to study antimatter as well, to really see what happens when it interacts with matter. So it's a known fact, even though it's something that we can't really see in everyday life.
Well, then I have a follow-up question, because then you always see only a reaction of the antimatter and matter, and you are right now trying to like catch the antimatter, or is it possible to catch it with the device you shown us, or have you already caught antimatter with the device?
Yes, so not with the actual device that I was using, but of course antimatter is being caught at CERN in several experiments. Currently the record for holding anti-hydrogen, so actually a neutral antimatter particle or particle system, would be 1,000 seconds. So it's really something that is done here at CERN for very many different reasons, either for looking at a spectrum or for looking at the gravity or magnetic momentum and stuff like that. So it's a pretty interesting topic.
Okay, and I got a note from studio that you, David, will not escape a question on you. And I think the question is coming from an audience, our audience. Can we get it on screen? And Mark Betta is asking, are you aware of the fact that there is a species of bee that uses sound and therefore vibration or resonance to get pollen out of a plant? So yeah, let's direct it to you.
Wow, that's like an awesome question for me because I love bees and I'm very interested to become a beekeeper once, but I never ever heard about this type of bee, and it will be cool to learn something from this. Thank you for getting my attention.
Yes, right.
There's a little bee.
Very bee-like demonstration there with the carbon dioxide. Thank you for that addition. And I would like to ask Michael now. That Michael, you mentioned that you are a Science on Stage ambassador. Is that correct? And if so, what does it mean? What are your responsibilities? Sorry, Michael, you are muted. You have to unmute yourself right now. I hope you can hear me. No, we can't. Yeah. Yeah, I believe Michael is giving us a really good answer, but unfortunately we can't hear it because he's muted in the software. So.
Okay, so now hopefully you can hear me.
Yes. Thank you.
Oh, okay. So I said, first of all, thank you for asking the question. So Science on Stage is a network of science teachers with the motto, from teachers for teachers. So it's all about sharing ideas, sharing teaching resources, creating things together. The shortest way of explaining it, for people who aren't familiar with it, I say it's kind of like a nerdy version of Eurovision, or like Eurovision for science teachers, because it's European based. There are national delegations which are selected through national competitions, and then they get together instead of every year, it's every second year. And then there's a festival, but rather than there being a big sense of competition, there's a sense of meeting other people, sharing ideas, sharing good practices. And so when I was in Prague as part of the French team, in April, or at the very end of March, and like the first day of April, that's actually when I met Alish and some people from Vita, and eventually ended up in Brno. Following activities there, then I was selected to be the ambassador for Science on Stage France. And it's a relatively new thing that they have ambassadors. There's not really a defined what you're supposed to do. It's more of like an honorary role than anything else. But for me, as much as anything else, the idea is to support and encourage teachers to work together, to share ideas with each other. And then, of course, to promote the network and encourage teachers to get involved with Science on Stage in their own country as well, and to run activities in a number of countries. The answer is pretty long already, but just to mention, in Spain, like this T-shirt I'm wearing, Ciencia en Acción, that's their national festival that leads up to Science on Stage. And when I'm done traveling here, I'll be going to Serbia, where I'm performing at the Belgrade Science Festival, but also co-animating stands at the festival with people from Science on Stage Serbia, and then running a number of workshops in collaboration with Science on Stage Serbia, including like a new workshop series I came up with called Science on Your Stage. And for that, I invite people from mainly all around Europe, kind of all around the world, to co-present either experiments or projects with me that, as need be, I'll either translate if it's a language I speak, and if they're speaking in a non-local language, or like in Serbia, it'll be people from Science on Stage translating it to Serbian, and we'll have materials on hand so that we'll be running experiments from, like last time we did it, experiments that were led by a teacher from Portugal, another one from a teacher from Greece, another from Bulgaria. So the idea, like really supporting people to share good ideas with each other and to make science more interesting.
Mm-hmm. Okay, thanks for telling us more about the project. And now I would like to move on, and I would like to ask if we have another question from audience, and if we do, can we please get it? Perfect. And we have Anya. have you ever felt earthquake vibration in CERN underground? And does it concern you? May I add?
I mean, I haven't felt any vibrations or any earthquakes underground at CERN. It's not something that would concern me because I'm typically not underground. And also there's no drilling around here that would cause that. So from that perspective, not. But there's an interesting fact that's related to that. Many things can be felt in the tunnels as well. Among them is the fast train between Geneva and France and Paris. And that one, when it passes this area here, you can actually see it on the beam. So the beam of particle actually moves because of that. So it's not an earthquake, though.
Yeah, sure. But it's still interesting. And if I may stay with you, I think I had a question from David, and it was about, or sorry, maybe it was from Adam, about how you prepared the device that you have. You said that you have it from your teaching lab that you have at CERN, and the question was, are the 3D models, digital models, available online, or is it a secret?
Yes, the 3D. So one of the main goals of CERN is to have everything open access. So yes, this Pole Trap can be found on School Lab's website, and of course will be found on Science Gateway's website as soon as the Science Gateway websites exist in full glory.
Perfect. That's
awesome.
Yeah, awesome to hear. So yeah, Adam was giving you a thumbs up for that. So thank you. And then I think I'll get back to Adam. And I have a master's degree in artificial intelligence, so I have to sneak in an AI question into this discussion. And the last few months were all about large language models. So these are the kind of AI that can create sentences that mimic human natural language. And they can express something that may concern some people. But on the other hand, a lot of people notice that they are great explainers. So they can explain stuff on various levels of difficulty and can and are used also in educational settings. And my question for Adam would be, if you've already used large language models in your job, in what way, and how would you, or how do you approach if your students use large language models for their assignments?
Yeah, I use it. I use it as teacher. I took some large amount of text and put it inside the ChatGPT and tell him that,
let's use it.
Tell it that it should be easier for one paragraph and easy to understand for children, like 15 years old. And it was all right. It was good. Like, short and right, because it was among my text what I put it there.
Yeah, it's great that you can actually fact check it. In a lot of settings people don't, and these large language models are known to not be factually correct at all times. But follow-up question would be, did you ever encounter your students using it for assignments?
Like a little bit, but I didn't have like a program or some activity like directly for using this ChatGPT or any kind of AI.
Okay. And I would ask our guests online if anyone has some experience using it. Please tell us more. Anya is nodding her head, so could you please comment on that?
Yeah, I actually used it as an experiment to find experiments, because one of the things that I want to show in one of the science shows would be quantum mechanics. And the fun thing is that the ideas that it gave were at the same time extremely ridiculous and very, very predictive. It was something that was very easy to see where it got it from. At the same time, it was so ridiculous that, it just made my evening for half a day.
Anyone else who would like to comment? If not, then I would like to follow up on this, as large language models are probably a part of the future of education. And there are some other technologies that might disrupt our current way of teaching stuff, teaching science and maybe other subjects as well. And my question for all of you would then be, if you imagine a future of education with all these technologies, with education on long distances, and what excites you the most about this future? What are you most looking forward to? And I would like to start with David.
Well, actually, I hope that I will leave education to others. So after I complete my master's degree, I will take a few years off, and I think that AI will, until that time, make its way, and I will find out. So no clue. I don't know.
Okay, thank you. And can I have an answer from Chris?
And the question was again, I have bad sound here.
Yeah, the question was, we see a lot of technologies that could change the future of science education or education in a whole. Do you see something that excites you in the future of education? Might be a long distance education, might be these large language models, might be other technologies.
Well, I'll tell you what, I want to turn to Stuart. What you did with the interference in the tubes, that simulation of the sound waves was fantastic. And I think that that type of simulation coupled with actual physical demonstrations continue to be the way we should teach. That's my personal feeling. I don't want everything to be computerized or simulated, but a marriage of the two, I think, is the way to go.
Mm-hmm. Thank you. Stuart, may I have your comments on this?
Yeah, Chris and I think, are very much on the same wavelength, if I can use that term this evening. And one of the things, so when I was working in the Science Center, we kept having, the internet is coming. It'll close science centers, we've got multimedia, it'll close science centers. And it hasn't happened. And it's probably not going to happen. These new technologies are all powerful, and they will find places, and they will change or disrupt, but probably change. What I've noticed is these new technologies, when they're used well, it's a case of this and the new opportunities that technology affords, that brings us. So kids these days, spending lots of time playing games online and virtual, but at the same time, the authentic experience of doing something physical, skateboarding, skydiving, all those sorts of physical activities, we're still living in a body, and how we learn and make sense of the world is still embodied. So the physical reality is always going to be richer than any simulation. But as perhaps you might have seen, sometimes those simulations can help clarify some things. So I will see it diversifying. What we need to think about is how we provide teachers and educators with the skills to choose the right tool, and not just go, ChatGPT, a new thing, we should do that just because it's new. We need to develop skills so that the educators, us, teachers, everyone, can choose the right tool at the time.
Mm-hmm, mm-hmm. Thank you. And now maybe Adam, apart from the large language models, anything else you can see that will disrupt teaching?
Disrupt?
Or be a part of the future of education?
I think we should focus more on fact-checking. It is trend even nowadays, but I think it should be, we should more focus on this topic also. And we should learn more to learn the principles of things, how things work, and not only memorize the things or memorize all the amounts of knowledges. Because you can find it. We should learn how to work with these knowledges that we can find.
Okay, thank you. I would like to have Michael comment on the future of education.
Well, I think one of the biggest things with technology, we already see that happening. You could call it the Zoom revolution, or the popularization of video conferencing technologies like we're using for this stream right here, and the potential that has for bringing people together. And it's technology that more or less has existed for a decade, but it took something like a pandemic to teach a lot of teachers and teach a lot of students as well how to get together and how to meet with other people and how to be able to share ideas that way. And there's a couple of ways it has a lot of potential for connecting people who might not otherwise get to meet physically or might not otherwise see each other. And I think one of my favorite things to do, and this is one of the things I do when traveling physically, like I'd love to travel physically and be new places, but is introduce people to each other or to make connections. And so that ability to make connections, I really think that's one thing that's going to become more and more prevalent and more useful as we move forward in education.
Okay, and then Anya, I wanted to leave at the last position because of one reason, because I was really excited about what you were talking when we spoke, and it was that you were mixing digital and physical technologies in your prepared shows, and I really like that. So I wanted to hear more about that, and also in connection to the question of the future of education.
Yeah, here I have to agree with Chris that what Stuart did is absolutely fantastic. Mixing both of those together is definitely the future. It will help everyone to imagine what's really happening on the inside of whatever, on the inside of the black boxes, or seeing the invisible things that we can't see. But if I connect to all the revolutions that are happening now, AI, fake AI, machine learning, stuff like that, I think one thing in all of this is going to be even more important, and I think it's already been quite visible during the pandemics, is that we will need to focus more on learning about nature of science. So what science is, not the final products, not the equations, not the, as many of you already said, not learning by heart, but really concepts and processes in science, so that people can make informed decisions and they can vote, if nothing else, with informed knowledge. So having critical thinking, knowing what people are saying, not necessarily, so you don't have to know everything about, I don't know, microbiology and biochemistry and stuff like that to understand if a certain thing, like I will go into COVID times now, so if a certain vaccine is good or not, because you need to know the science behind it. So just the processes that make us say, yes, this is something to be trustworthy, or no, this is not to be trustworthy. And I think with the dawn of ChatGPT and similar, who are just not able to distinguish between truth and absolute lie, I think this knowledge is going to be of the utmost importance. And I hope, really, really hope that public education systems will be able to adapt to that in less than 100 years.
Thank you very much. Thank you all for commenting on this question. And I think this discussion sparked some very interesting conversation about the future. I think there are a lot of ideas about mainly human connection, human parts of the education, which may be overshadowed by the technology when people talk about it. And I'm grateful that it came up here so often. And my personal hope is that this technology will actually allow more people to be in the education, because they can add what the technologies can't, and that is the human touch. And so again, I would like to thank all of you, all of our perfect guests that had brilliant performances here, and also to our team, Science On, that made this possible. And we have Shimon behind camera, we had Aleš in the sound, and we have Janet, who was directing it, and also Adam here performing. So thank you all, and I would like all you to follow Science on major social media platform. We are streaming once a month in Czech and once approximately every 6 months in English. And as Eurovision was brought up here by Michael and not by me, I can say something that I was hoping that I could have chance to, and that is the opening of Eurovision, which is closing for us, and that is good night, Europe, and good morning, Australia. So thank you again for listening. Thank you again for watching the stream, and you will see cut-it versions of this later. Goodbye.
Thank you. Bye.
See you guys.